and welcome to the first ever ElixirZone. I'm James Lavin. I'm a former Ruby developer who discovered Elixir about 7 years ago and never turned back. I love Elixir. I love Erlang. Haven't used Erlang professionally, except it is the foundation of Elixir, so when you get deeper into Elixir, you start digging into Erlang. But most of the code that I write is Elixir. I love it. I don't ever want to do anything else, and I want to explain to you why I find it so exciting and why I think it is an interesting language for you to discover as well. For me, Elixir is about happiness. I enjoy it. I find it very easy to work with, very easy to understand, far less likely to have nasty bugs that cause me to tear my hair out. And I've been making a good living off of it for the past 7 years. And I think it's something that you will enjoy as well. So I'm excited to share my love for these two languages with you and the ecosystem that's grown up around them, which actually is bigger than these two languages specifically. And we'll get into that. So after I discovered Elixir, I decided to push all my chips into the center of the table. And I have actually succeeded beyond my wildest dreams in terms of how the ecosystem has continued to evolve and improve. I feel like this character from one of my favorite shows, Schitt's Creek, which I highly recommend you watch if you haven't seen it. It's hilarious. Raking in the chips every day. I can't imagine life without Elixir at this point. I wouldn't really consider another job that doesn't involve Elixir. I just love it that much. Elixir is often considered a functional programming language. I think the main thing, which I'll be talking heavily about today, is that it's a highly concurrent language. But let me start off by, Alan Kay is a famous programmer, software engineer who coined the phrase object-oriented programming and objects. And somebody on Quora once asked what Alan Kay might think about Joe Armstrong, the creator of Erlang, one of the creators of Erlang, claiming that Erlang might be the only true object-oriented language. And Joe's thesis advisors claim that Erlang is extremely object-oriented because most people don't consider Erlang, which is the underpinnings of Elixir, to be object-oriented. And interestingly, who weighed in to answer this question but Alan Kay himself? And Alan Kay said, who knew Joe Armstrong before he passed away? They were friends. They interviewed each other. I love Joe Armstrong. We lost a great man when he left us recently. And he might be right. Erlang is much closer to the original ideas I had about objects and how to use them. I encourage you to watch some Alan Kay lectures because he's a very creative guy with he's a polymath. He knows all kinds of things, and he brings different ideas from different domains together in very interesting ways. Fascinating guy. One of the interesting things about him is that the reason he loves the Erlang model of programming is that it is completely message-based, and the reason he thinks that's what he had in mind when he talked about objects originally, and it's because he comes from a biology background. He started off as a biologist. He sort of worked as a supercomputer programmer in his early days to pay the bills, but his love was for mathematics and biology, and he thought he was going into biology and ended up in software engineering. But the reason, the idea of the Erlang concurrency model and processes and objects, which Erlang doesn't call objects, but Alan Kay said and Joe Armstrong both think of as objects. These Erlang processes act very much like human cells in biology, where in a typical programming language, an object could call another object. You just reach out, push a button, basically call a function directly on another object. In the real world, cells don't operate that way. Cells don't reach out to other cells and push buttons to make things happen inside the cell. What they do is they send messages. They can send various kinds of hormones, etc., or neurotransmitters, or whatever it might be. They send messages that may or may not be received by the intended recipient, and the intended recipient can ignore the message or do something in response. It's up to the recipient what, if anything, it wants to do in response to any message it receives. So this is a natural model that Alan Kay had in mind, and it fits the Erlang processes model, which I will explain now. So here's a simple diagram of how Erlang does process management. So a process is completely isolated from every other process inside an Erlang system. And again, Elixir is built on top of Erlang, uses all the same primitives. So I'm going to be talking today about Erlang, but pretty much everything applies to Elixir as well. So you have two independent processes, and they each have their own completely private memory. No memory is shared. Even the messages that get passed from one process to another are not shared. They don't have a pointer to a message somewhere. What they have is the Erlang will copy each message. When process 1 wants to send a message to process 2, Erlang will copy the message and give process 2 its own copy of that message. So nothing is shared in Erlang. Everything is completely isolated. Every process is completely isolated from every other process. And this buys tremendous benefits. One is that if a process dies, nothing else is directly affected. So if process 1 dies here, process 2 can continue on. You don't have cascading failures. A second thing, and so that enables recovery from failure. So you could have another process which is responsible for monitoring process 1, and it detects that process 1 has crashed, and it will restart a new replacement process 1 to do the same job. There's many things that Erlang can do because of this very simple model. And because the memory is completely isolated from each process, within each process, Erlang's virtual machine is able to parallelize work across all the cores on a CPU, across multiple machines even, safely, in such a way that if any machine or any single individual process dies, it doesn't cause cascading failures. Let's move on here. So this is a slide from Martin Odersky, who is the creator of Scala and did a lot of other famous things in programming. From 2012, I believe this slide is from. And he said that mutable state plus parallel processing is the root of non-determinism. And if you're a programmer, if you've been programming a while, you don't like non-determinism. Especially, we get into things like race conditions and all kinds of very tricky problems related to bugs that are very hard to debug. And so his response, Martin Odersky's response to this problem, was to basically try to replicate the approach that we saw Erlang adopt with processes that are completely isolated. Scala has what's called the ACA model, which I have never used, but I've read a bit about it, and I'm no expert on this, but it basically is using what's called the actor model. The actor model was invented by academics in the 1970s. The Erlang people in the 1980s and early 1990s who created Erlang did not know about the actor model, but they basically invented, what they built was an implementation of the actor model, and that's sort of these independent processes. It's called the actor model because if you think about human beings, for example, communicating with each other, we don't push buttons on each other to say, do this, do that. We can communicate with one another using messages. So we speak to one another, for example, or we can send each other an email, whatever it might be. The information inside our brains is not observable directly by anyone else. The information in our brains is our own personal state. We receive messages. We can intentionally or unintentionally ignore them. We can respond to them however we choose. So each of us is effectively an actor. We have self-contained state, which is encapsulated and private to us. People can send us messages. We can send other people messages. And it's inherently asynchronous because it takes time for messages to go from place A to place B, even if that is the speed of light or the speed of sound, whatever it might be. The world is full of asynchronous messaging between actors, really. And that is the model that academics in the 70s came up with. It's the model that Ericsson, when it tried to build a reliable telecom system in the 1980s, basically landed on, because they couldn't find anything that solved the problems they were trying to solve. And you can see the ACA model from Scala has borrowed some of its, even some of its syntax is borrowed from Erlang. But it was very much an attempt to replicate some of the benefits that Erlang offers. Here again, this is ACA. This is an ACA actor. It looks very similar to what I just showed you with an Erlang process. You have a message queue. I didn't mention that earlier. Let me go back to the earlier slide. So in Erlang, you have each process has a mailbox. So when messages come in, you could get a whole bunch of messages all at once that you can't deal with them simultaneously. A process at any given moment is processing a single message. Any messages that come in while the process is busy processing some other message, or while it's been put to sleep by the virtual machine, which can happen. That's another benefit of having these individual processes with their own isolated state, is that if any process is busy for too long, the virtual machine can just pause them. The state is all in one place, so it just pauses the execution of the process, lets some other process have its turn, and then eventually it'll come back to it. Or if there are no messages in the mailbox of that process, it will put the process to sleep so it's not consuming resources. And then when that process receives another message, it will wake the process up and say, okay, here's your chance to deal with this new message. But these mailboxes allow for the ability for messages to queue up and to be processed one at a time. The earlier version of the Erlang's predecessor, which was also in use at Ericsson and served as sort of a model for some of the ideas that are built into Erlang, did not have, it had individual processes, but it didn't have mailboxes. So every message had to be handled as soon as it arrived, the moment it arrived. And that caused all kinds of problems. So part of Erlang's innovation was discovering this concept of a mailbox. So again, ACA has taken the idea of an actor or a process which has a mailbox, and then a message handler that will process each message one by one. Again, I'm not an ACA or Scala person, but this article, which you can read, suggests that the ACA implementation is not inherently safe as the Erlang implementation is, because ACA does not completely follow the pure private state that the Erlang processes have. There are ways to do unsafe things with ACA. Synchronous messaging is one of them, and the fact that it mixes with object-oriented programming. Therefore, it's possible to expose the internal state of an actor through publicly available methods. And that's without using messages. So in Erlang, processes can only communicate through messages, and the memory spaces are completely isolated, which makes it completely safe. As I understand it, in ACA, that's not necessarily true. You could program that way, but ACA does not force you to. And if you leave that sandbox, you may no longer enjoy the safety provided by the actor model. So I'm not here to slam ACA or Scala. I don't know them very well, but I just want to point out that the Erlang actor model is a very powerful paradigm, and so much so that Martin Rudirsky, a brilliant guy, decided to use it to create ACA, which is in widespread use. It's terrific, but even their implementation is not as safe as the Erlang implementation. I like this meme. I made a variable mutable. Now I can't share it without synchronization. And that is really the crux of the problem. When you have shared mutable state, if you have shared state, but the state is not changing, it's immutable, that's okay. You can have multiple processes reading the same information as long as nobody's ever changing it. Similarly, you can have mutable state that's not shared. So that's like within a single process, where nobody else can reach into the internal state of that process. So the process itself can evolve its own state over time, but no other process can directly access that state. So that's mutable state, but it's not shared. The problem is when we get to shared mutable state. When you do that, you need to use synchronization methods to prevent multiple simultaneous interactions with that data, and that causes all kinds of challenges and problems. And I'm not a smart enough engineer to figure this stuff out. I just don't want to deal with it. I like Erlang's simplicity, which protects me against all these problems. But most languages out there, the object-oriented programming languages that are very popular, they have all kinds of different ways to try to avoid this problem. Locks, mutexes, semaphores. And you can do this, but you also can end up shooting yourself in the foot in ways that are extremely hard to debug. And I just would rather avoid that completely, as the Erlang team also did. So many languages, this is hardly a comprehensive list, but many popular languages, most popular languages use shared mutable state. And again, there's nothing intrinsically wrong with it. It's just dangerous. It's dangerous by default. I prefer the Erlang Elixir model, where it's not possible to have shared mutable state, which makes programming in Elixir and Erlang kind of boring in that way. But I like this form of boring. So here's a diagram from a book called Intro to Concurrency in Programming Languages. I want to define the terms concurrent and parallel because it's confusing. So concurrency is about processes. So could these multiple processes happen simultaneously in the real world or within the virtual machine? Is it theoretically possible for them to run at the same time? And most languages like JavaScript, let's say JavaScript's event loop, in the event loop, it appears as if multiple things are happening simultaneously, but what's really happening is that execution is happening on one thing, and then either that thing ends and something else, execution of something else starts, or maybe that thing could get paused and then something else happens and then it comes back to that same process a bit later. So you have three different things that in theory could be happening simultaneously or asynchronously. But because you're limited to a single thread of execution, you have to split up that thread and share it across all the different things that you want to be doing. And so each thing can only happen part of the time, even though, when you're not looking at the CPU level, as a human being looking at your computer, it feels like all these things are happening simultaneously, but in reality, they're not. They're being interleaved. Parallel execution allows you to say, okay, these things that in theory could be run simultaneously, let's actually run them simultaneously. And in that case, you can see that this x-axis is time, and so it takes much longer to execute these concurrent tasks in a non-parallel way than it does to execute those same concurrent tasks in a parallel way. The problem is that executing concurrent tasks in a parallel way is dangerous if you have shared mutable state, because things blow up. And they can blow up in sometimes easy to debug ways, but often in very subtle, hard to debug ways. And this is why, so I mentioned the event loop. Here's an example. So you can say, oh yeah, but JavaScript or Node or whatever it might be can do all kinds of other things as well. And that's true, but it doesn't do it on that main thread or the main event loop thread. What it does, it receives lots of requests, and it needs to do all kinds of other stuff. And what it basically does is it says, okay, I need to call out to a database now. Let's have someone else do that work, and then let me know when the work's complete, and then I'll pick up the handling of it at that point. So you can have additional threads doing other types of work. Similarly, I/O, printing something to a screen, saving something to a file, reading from a file. All these things can happen off the main event loop, but there's only a single thread for the main processing of information, and that's because it's dangerous to do things in a truly parallel way. And so instead of doing that, they will have a single thread of execution for the main work and use callbacks to offload work to other threads that are safe to do separately, like a database call, isn't going to affect any data in the system until you put it back into your system. So, this approach is fine, but we're going to realize that it causes all kinds of challenges for scaling, and I'll explain that soon. So WhatsApp in 2012 put out this blog post, and they said that they had a single server that was hosting over 2 million simultaneous TCP connections. And they were doing that on the server using only 38% of their CPU, which is pretty impressive. WhatsApp was built with Erlang. Erlang has massive concurrency. So these processes that I mentioned earlier are not typical. When we think of processes, we typically think of operating system processes or OS processes, which are heavy things that have to be scheduled to a CPU thread and basically own that CPU thread while they're executing. The Erlang processes are not that. They are completely different. They are created within the virtual machine, which is called the beam, but the virtual machine that runs Erlang can create millions of processes, completely isolated in terms of memory space, able to start and stop and pause execution, and it's all managed not by the operating system but by the Erlang VM. And so that's what app was doing here. So they had over 2 million different users connected via TCP to a single server, and each of those connections had its own Erlang process under the covers, communicating across that TCP connection. Phoenix is the Elixir framework, the Elixir web framework built on top of Elixir. So Elixir is built on top of Erlang, Phoenix is built on top of Elixir, and in 2015, Phoenix framework was able to do something very similar, where they had 2 million simultaneous WebSocket connections to a single Phoenix server. And that's the sort of thing you can do in Erlang that's extremely hard to do in programs in languages like Ruby or Python to make this completely safe. And if any of these WebSocket connections died, nothing else gets affected. The other 1,999,000, etc., WebSocket connections would be totally fine because they are completely isolated from one another. So if anything goes wrong, only that one little process blows up and everything else continues working smoothly. Interestingly, I don't seem to have the slide here, but I know that they said that the only reason they had to stop at 2 million WebSocket connections is because they ran out of, I think, file handles within Linux. They could have gone higher than that. The name Erlang comes from Agner Erlang, who was a mathematician, statistician, and engineer in the early 20th century in Denmark. And he created the field of telephone network analysis. And that's where he invented what's called the Erlang Formula, which is a key element of modern telecom network studies. I should have shown that a second ago. Let's try this again. Okay, and so there's a unit of measurement called the Erlang, which is what Erlang is named after. It also sounds like Erlang came out of the company Ericsson, so it also sounds like Ericsson language, and it's an interesting pun. But supposedly this was the true foundational inspiration, but it has multiple reasons for being the name of the language. So carried traffic in Erlangs is the average number of concurrent calls. See the word concurrent there, that's the key. Measured over a given period, often 1 hour. We don't need to go into offered traffic, but it's a similar concept. So this was named the International Unit of Telephone Traffic in 1946 in this man's honor. So the Erlang is a measurement of concurrency, which is why it's such a fitting name for this language, which is all about concurrency. This is there's a number of presentations given by the Erlang creators. This is Robert Verding. He's one of the creators. The three main creators are Mike Williams, Robert Verding, and Joe Armstrong. There were many others involved, but they were the three most famous and most heavily involved. So he gave a talk in 2016 where he explained the problems that they were trying to solve. And he's very clear that what they were trying to accomplish was true telecom business needs that were challenging to Ericsson. They needed huge scalability. Well, let's go through the points. So these were business requirements that came out of the challenges that Ericsson, the company, faced. So actions must be performed within a certain amount of time. So you couldn't have very slow things. Like in the JVM, garbage collection can often be stop the world, I've been told. And Erlang couldn't have stop the world garbage collection, for example, which causes like the 99th percentile of behaviors to happen really, really slowly. Couldn't allow that. The system must be distributed across several computers. There's multiple reasons for this. One is scalability, but another is fault tolerance. Because if you run something on a single computer, there's no way to guarantee reliability. You need to have at least, Joe Armstrong made the point, you need at least 2 computers to be reliable, because a computer can crash at any given moment. The system is used to control hardware. The system can become very large. The system can be very complicated and have lots and lots of features interacting, which is why they wanted modularity, so that complexity didn't explode. Systems needed to be in continuous operation for years. Erlang was built so that you could upgrade the software without bringing down the system. Hot code reloading, it's called. Software maintenance should be performed without stopping the system. Stringent quality and reliability requirements. Fault tolerance, both to hardware failures and software errors. So if things blow up, either because the server died or because the software was wrong, somebody put a code into production, the system needed to keep moving and not fail. And the system must be able to handle very large numbers of concurrent activities. So they were building telephone switches which would have thousands of users connected through the switch. And if any of those connections had a problem, nothing else should be affected. And they needed to be able to scale to have thousands or tens of thousands of users using a single switch. So this is a very difficult set of requirements. And interestingly, although they were pretty unique challenges back in the 1980s and 90s, they've turned out to be very similar to the challenges that we face with scaling web servers, etc., in modern programming, which is why Erlang is relevant to this day. So Robert Verding, he emphasized that they didn't plan out to build the actor model. They didn't even know that the actor model existed. They didn't set out to implement a functional language. They were dealing with a set of very concrete business requirements, and they were trying to solve those problems. And what they discovered the solutions to be after a series of, after several years of repeated testing and development and retesting and all these things, they landed on these key principles. Lightweight concurrency, so that's being able to have hundreds of thousands or millions of processes simultaneously. The creation of the process, the switching between processes, and the communicating between processes must be cheap and fast. Communication had to be asynchronous. You couldn't have, one process waiting on another process to respond. The primitives in Erlang allow you are asynchronous. You can add a layer on top of that and make things synchronous just by having your caller block and wait for a response from the receiver in a client-server model. But the primitive built into Erlang is asynchronous. So you can add synchronicity on top of it, but you don't have to. It's by default asynchronous. Processes are completely isolated from one another. If one process dies, it can't affect any other process. Error handling, when something goes wrong, that failure needs to be detected and handled. So there's supervision trees and processes supervising other processes, so that if anything goes wrong, the error gets detected and handled. The system needs to evolve continuously. They need to be able to upgrade the system while running, and nothing should block. Things should happen pretty quickly. Things should never be super slow. Francesco Cesarini is a very big. He's a great guy in the field. He's been advocating for Erlang and recently Elixir for many years. He's been written several great books on the topic, and he said instead of inventing a language and then figuring out what to do with it, they did the exact opposite. They weren't setting out to invent a language. Well, he says they weren't even trying to invent a language. They first searched for a language that did what they needed, and after trying everything, they found that nothing did what they needed. So then they started inventing a language that solved a very specific problem: massive scalability and reliability. Phone networks were the only systems at the time who had to display those properties. This chart will explain why Erlang has become increasingly relevant over the last 15 years or so. What you'll see is that the clock speeds of CPUs has basically been flat since about 2005. This used to be where we got most of the performance gains, is that CPUs kept getting faster and faster, but they're no longer getting faster and faster because they've hit the laws of physics. And the way they've been able to make CPUs more powerful is by sticking more and more transistors into them, but by adding more and more logical cores. So instead of having a single CPU thread that's really, really fast, you now might have 8 cores on your CPU, or 16 cores, or 64 cores on your CPU. And each of them may be as fast as a CPU was 15 years ago, but you have 64 of them instead of 1. And this enables, if your program can run in parallel, you can parallelize the work and get 64 times as much work done. But if you have a programming language that has an event loop, or we'll get into something called the global interpreter lock that Ruby and Python have, you can only use a single core at a time, except for the stuff that you're offloading to other independent threads like I/O, etc. So basically, you're stuck with a single thread. So your CPU speed, performance, this is hitting you very, very hard because you're not benefiting from any of the advances in microprocessors over the last 15 years. In order to benefit from microprocessor improvements, you need to be able to parallelize your work. And Erlang out of the box does that. So a global interpreter lock is something that languages like Python and Ruby use to synchronize the execution of threads so that only one native thread can execute at a time. An interpreter that uses GIL, a global interpreter lock, always allocates exactly one thread to execute at a time, even if run on a multi-core processor. So they're intentionally not using the other cores, because if they parallelize their work and use multiple cores, they hit the problems that synchronization is required to prevent shared mutable state from blowing things up. So to prevent shared mutable state from blowing things up, they use the global interpreter lock to prevent parallel execution of their code. And that obviously hampers performance of Python and Ruby in this age where CPU performance enhancements are 99% happening through the addition of additional CPU threads rather than making an individual thread faster. This is a great article. I read this last night. It's like 20 pages of the history of Erlang by Joe Armstrong. Fascinating about the challenges that they faced, how they worked through them, how the language evolved over time. If you're interested in Erlang, highly recommend this paper. I'm going to quote a couple things from his paper. So first he says, Erlang was designed for writing, this is how he describes Erlang. I think it's a great summary. Erlang was designed for writing concurrent programs that run forever. Erlang uses concurrent processes to structure the program. These processes have no shared memory and communicate by asynchronous message passing. Erlang processes are lightweight and belong to the language, not the operating system. Erlang has mechanisms to allow programs to change code on the fly so programs can evolve and change as they run. Brief history of Erlang. So in 1985, Joe Armstrong was hired and he asked, what should I be doing? And he was told his job was to solve Ericsson's software problem, which was a little vague. He interpreted it as find the language that will make our telecom switches work. He, after exhaustively evaluating every language out there, especially the ones with concurrent in their names or their descriptions, they basically discovered no such thing existed, so they started building their own. Oops, went the wrong way here. So he started working on adding concurrency to Prolog. Eventually, over the next couple of years, he and Robert Verding and I think Mike Williams landed on something that approximates Erlang today. They evolved their Prolog interpreter into what is similar to Erlang. In 1990, they built a compiler, and Mike Williams built an emulator, made it about 70 times faster. So it was getting usable at that point. The next year, they started working on distributed multi-node Erlang, which is something they had always wanted to do, but they had never gotten around to starting it. In May of 1993, they published the first Erlang book, which came out, and they also created the Beam virtual machine, which was a lot faster than the Jam stuff that they had made a few years earlier. Erlang Systems was created. I think Francesco Cesarini is the CEO of Erlang Systems today. Erlang Systems launched to train, consult, and document Erlang. The first distributed Erlang product happened in 1995. In the end of 1995, Erlang was suddenly embraced within Ericsson, and OTP was launched. And this happened because of a fortuitous event inside of Ericsson that led basically a big project that was not using Erlang called AXEN failed. And at that point, the management decided, okay, we're gonna try this Erlang thing, and worked really well until a few years later. Even though it was a massive success, Ericsson decided to ban Erlang. And the reason Ericsson decided to ban Erlang is because they felt that it was proprietary and they didn't want to have the burden of having to maintain this language over time without any external help. They thought it was a dangerous situation to be in, where they were building mission-critical business products on top of a language that they were completely responsible for debugging and maintaining. So at about that same time, the product that was built with Erlang was a massive success. It had over 1 million lines of Erlang inside of it, and it had a 9 nines availability, which means basically it was off. It was down for seconds or minutes per year. It was a spectacular success. Erlang over-delivered. The product was a huge success. But Ericsson still didn't want to use Erlang anymore, and they said, we're not going to use it in any new products, and the existing products are going to have to phase out Erlang. So people within Ericsson convinced Ericsson management to release Erlang as an open source project, which is sort of a new thing back then. And many of the people working on Erlang quit, and they formed their own company called Bluetail. A few years later, Bluetail was bought by Nortel, which back then was another big telecom company. Eventually, years later, in 2004, Ericsson lifted the ban on Erlang, and Joe Armstrong and others went back to Ericsson. In 2006, symmetric multiprocessing was added. So that's the ability to use multiple cores. So Erlang, because it had completely isolated memory for each process, and because messages that got passed were passed by copying rather than shared pointers to messages, it was able to parallelize work. But even though it had in theory been parallelizable up until then, they hadn't gotten around to actually making the execution parallelized. In 2006 they did, and that opened up all kinds of possibilities and performance benefits. This is where the Elixir piece of the story sort of begins. The man on the left there is Joe Armstrong. The man on the right is Jose Valim. And Joe is sort of the main guy behind Erlang, and Jose is the main guy behind Elixir. And they became friends before Joe's passing. Joe had tremendous admiration for Elixir and what it was doing, and thought it solved some of the challenges and limitations of Erlang. Elixir brought a lot of extra tooling and developer happiness to Erlang, among other things. I didn't. This is a brief history of Elixir. I'm not going to go too much into it, but he started building it in 2012. Chris McCord, and both Chris McCord and Jose Valim were Rubyists who grew frustrated with Ruby's model of concurrency, and because it basically couldn't do parallelism. Both of them. So Jose went looking for a language that did concurrency better, and he found Erlang and decided to build Elixir on top of it. Chris McCord, similarly, he built some concurrency tools within Ruby that just didn't work right. He couldn't get them to work right. And so he went looking and discovered Elixir and fell in love immediately and decided to start building a Phoenix web framework on top of Elixir. And the first thing he built with that was Phoenix channels, which leverage Erlang processes under the hood. That's when we get to the 2 million WebSocket connections. Phoenix Presence was added, and now Phoenix Live View, which is amazing, but I won't be talking about today. But this is a great article that sort of summarizes the history of Elixir and Phoenix, how we got to Live View. It's by Chris McCord, the Phoenix creator. Great summary of that there. Elixir and Erlang are not the only languages in this ecosystem. There's also LFE, which is Lisp-flavored Erlang. There's also Gleam, a new language that, as it says, it's a friendly language for building type-safe, scalable systems. It compiles to Erlang and has straightforward interoperability with other Beam languages such as Erlang, Elixir, and LFE. So this is a whole ecosystem. There are a number of other languages that aren't as famous that run on the Beam. Well, Lua's kind of famous. So it's a whole ecosystem now. And this ecosystem has its own foundation now. Which is fabulous because it's bringing people together from the Erlang and Elixir sides and the LFE, etc., to all work together and make the whole better than the sum of the parts. And this Erlang ecosystem foundation has a variety of working groups, and covering various topics such as language interoperability, observability tools, machine learning, documentation, education and training, security. It's fabulous. The way the ecosystem, a lot of Erlang developers have become Elixir developers. A lot of Elixir developers, like myself, have been learning Erlang, and it's just making everyone, giving everyone more and more power and knowledge. I won't waste more time on global interpreter lock, but you can read this. It is a bottleneck for languages like Python and Ruby. Here's a beautiful. This talk is amazing, and the first thing after you watch this talk, if you're excited, I highly recommend you go watch this talk by Sasha Jurich, who is a legend in the Erlang and Elixir communities. He began as an Erlang developer. He does all Elixir now, but he knows things brilliantly, and he has written a number of books on the topics. This talk is brilliant. One of the things he shows here in this diagram is, so he's using a single scheduler. So we said you can parallelize work in Elixir and Erlang, and that's true. But you get some benefits just with, even before you have multiprocessor parallelization, you get some other benefits. So in this example, he intentionally codes a bug, and it causes the process to go into an infinite loop. And the infinite loop is just consuming that one CPU thread that he's artificially limited the Erlang virtual machine to use. But all the other jobs in the system are still succeeding at the same time. So the scheduler is pegged at 100%. The CPU core is pegged, but all the other jobs other than this infinite loop process are still getting processed properly. And the reason is because the Erlang VM is repeatedly pausing execution of this infinite loop process and letting other jobs have their turn. So even though a process is in an infinite loop and there's only one scheduler, everything is still working perfectly. You wouldn't even know that there's a bug unless you looked at the CPU and saw it was pegged at 100%. So the ability to really isolate each process and what it's doing, its memory and its execution, and pause and unpause its execution creates tremendous benefits, even if you have only access to a single CPU thread. Again, this history of Erlang paper is great. Joe said, what we would like is a way to explicitly manage the set of remaining goals of a busy process so that we could suspend or resume the computation at any time. A reduction machine works by successively replacing the top of the stack by its definition, or if it's a primitive, by evaluating the primitive. The point of the reduction cycle is that at any time we can suspend the computation. If we want several parallel reduction engines, we arrange to save and store the states of each reduction engine after some fixed number of reductions. And because we have multiple processes, even though we have an infinite loop when we try to execute this, another process can detect the error and handle it appropriately. So instead of this display blowing up, another Erlang process has detected that there is an error, or that the process that's doing the actual calculation is not returning a value, and so it can display an error message. So this is how we handle errors by relying on multiple processes. So if something goes wrong with one process, other processes can still recover from that situation. So this whole display doesn't blow up because you put in an input. We're trying to do an infinite loop and we're never going to get to the end result. You can still handle that software bug. These are the three creators of Erlang: Robert Verding, Mike Williams, and Joe Armstrong. They've given a number of talks. I highly commend those talks to you. I'm going to start showing some hands-on examples of Erlang and how we use it. In later videos, I'll focus mostly on Elixir, but for the first few videos, I'd like to show you some Erlang. I think it's valuable for Elixirists to see some Erlang and feel comfortable with it, in part because there are all these great books on Erlang that teach you things about OTP, which we haven't talked about yet, but there are things that you would want to use in Elixir as well. But the original documentation is written in Erlang, so being able to read the documentation in Erlang is tremendously beneficial. Similarly, you can use Erlang code within your Elixir code. So there's a lot of benefits for Elixirists to understand Erlang. So we're going to do some simple Erlang coding soon. But this is from a famous video that they made at Ericsson back in the day, where they called each other because it was a telecom company and they were doing network switches. They called each other and said, "Hello, Robert. Hello, Joe. Hello, Mike." It was actually pretty funny. They didn't intend it to be funny. They actually thought it was a very serious thing, but it's become sort of feels very Monty Python-esque. In hindsight, everyone has a good chuckle over it. But we'll implement this in Erlang. Don't know why I got that in there too. Let me start by introducing a few simple concepts here. So this spawn is a function that will execute. So f is an Erlang function. So this is spawn is a function call, which is receiving a function. So capital letters are variables in Erlang. So this is a variable holding a function. We are spawning a new process, which is supposed to execute that function. That's what spawn f is saying, is create a new process, brand new process, and have that process execute the function f. And then the result of calling that spawn is first of all, it will create a new process, and it will return to the code here the process ID of the newly spawned process, which is basically the address to which you can send messages. So it's the mailbox address for that process. Then this bang operator is allowing you to send a message. So capital letters again are variables. So we have a variable m, which in this case it can be any any Erlang data structure. It can be sent as a message. So this is just some arbitrary Erlang data, which we are sending as a message. That's what the bang operator is doing to this process ID that we just captured here. So we created a new process by spawning. That process is running the function f, and we're getting the address back for that new process. Then we are taking a message, which is a data structure in Erlang, and we're sending it as a message to that process. And then within the process itself, this is sort of part of the function f in this case. So we're saying start the new process and run this function, and part of this function would be this receive. What the receive is doing is it's saying, okay, wait until you get a message. If you get a message, now start trying to match those messages. If you receive a message that matches this pattern, then do this thing. If you receive a message that matches this pattern, do this thing. If you receive no messages after time, however many microseconds has passed, then do this thing here. So this is what's called selective receive. So the process is waiting for a message. If it has no messages in its mailbox and it has received no messages, the virtual machine will probably put it to sleep. When it does receive a message, the virtual machine will wake up the process and say, okay, here's a new message for you, try to match it. And it will go through and take actions according to whatever type of message it received. So with that, I think we can move on to actually code some Erlang. Okay, so let's start learning some Erlang. As you can see here, I've prepared a couple of small Erlang programs, the first one being called joe.erl. ERL is the Erlang source file extension. So let's open this up and see what's in there. It's going to look, Erlang syntax is a little odd. Most people find it unintuitive, and that's one of the reasons Erlang never really took off in a major way. And another reason that Elixir was sort of built on top of Erlang. Nothing wrong with Erlang syntax, it's just very unfamiliar to people. So let's work our way through it. First of all, everything ends with a period. You can, if you have a thing, so here's a function receive loop that ends in a period, but it's broken up into smaller statements, which are separated with commas. So that's the first thing to notice. So at the head of your file, you're going to name the module. In this case, we're saying this module is named Joe, which is why I called it joe.erl. The next line is saying that we're going to export two functions. So that's going to make these functions callable. So start, the 0 here is the arity of the function. So a 0 arity function is invoked with no arguments. A 1 arity function is invoked with a single argument. So we're exporting these two functions. In Erlang and Elixir, you can have multiple clauses with the same for a function with the same number of arguments, and they are considered the same function. But you can also have the same function with different arities, and in that case, they're sort of separate functions. So you could have a start 0 function, and you could have a start 1 function, and you could have a start 2 function. In future videos, we'll show some of that. And then this thing here is version. So this is saying this is version 1.0 of the Joe module. I'm not going to right now upgrade this, but I'm going to upgrade it in a couple of minutes, and we'll see how you can do a different version. So what I'm doing here is I'm going to invoke this. It's called receive loop because we will be turning it into a loop in future videos, but right now it's not actually looping. We have three functions. We have call, which is expecting a single argument. Any variable that starts with a capital letter is a variable. So this, when you call the call function, you will pass in a single argument. It will then call the IO module, just like this is the Joe module. There's an IO module. This colon is saying, okay, everything to the left is the module name. So the IO module has a function called fwrite. And since this is taking two arguments, fwrite should be able to have a 2 arity version of it. The first value that we're passing in is this string, and the second thing that we're passing in is a list of arguments. In this case, there's only one element inside the list, and it's arg1, whatever was passed into the function when it was invoked. Receive loop is going to do 3 different things. First, it's going to create this, I'm calling it string. I think it's called a binary in Erlang. It's a little different from Elixir string. We'll get to that when we get to Elixir, but for now I guess we can call this a string. It's really a binary. We're going to turn that binary, the data that we're going to pass as the message is that binary. That's all there is in the message. We're going to send that message to Robert. So we haven't yet looked at Robert, but there's going to be another module which will be spun up as a process named Robert and registered as Robert. You can send messages to PIDs, the process IDs, or you can send them to registered names. So you can associate a registered name with a process. So when we start Robert, we will get a PID and associate its PID with the name Robert, which is its registered name. So the first thing, when this receive loop starts, it's going to create this message, send it to Robert. And then it's going to go into a receive, and it's going to wait for a message. And once it receives a message, whatever that message is, because this will match anything, and we're looking to match things. And since this is there's no pattern here other than any message at all, we're going to write Joe received a message, and then the way this works for fwrite, it's going to take the first value in this list, in this case the only value in the list, and put it in place of this tilde p. The tilde n is just a line break. So it's going to write Joe received a message and then put the message there and then a line break. And then after it prints out the message, it's going to then create a new message, which will be in a different string. Hello, Mike from Joe, and it will send it to Mike. And then it's going to wait again. And then when it gets another message, it will then do another write where it says Joe received a message, and it will put the message in there, presumably from Mike. And this is the function that we are going to call. We needed to export it in order to be able to call it. So we're going to call this by Joe:*start. And since it's a zero-arity function, we don't pass in any values. And so when we invoke Joe:*start, it's going to do these two lines. The first, and again, they're separated by a comma and ended with a period. The first thing is it's going to spawn a new process. And the process will, did not want to do that. The new process will run this anonymous function. The anonymous function is going to do two things. You'll see there's a comma there. So it's going to call the call function with the value Joe has arrived, which will simply print out Joe has arrived and then a line break. And then the second thing it will do is call receive loop, which in this case is not really a loop. It's just sending a message and then waiting for a message to arrive, printing it, sending a different message, and then waiting again. And when it receives its second message, it will print that, and then that function will be over. And since we're not looping, once you get to the end of all the things that you can do as a process, you die. So we will spawn this process, we will grab its PID, we will then register that PID. As I mentioned earlier, that PID will be registered to the registered name Joe. So any other process in the system will be able to send a message to Joe via its registered name or its PID. Either way, the message will get to Joe. And the messages, since Joe will immediately enter into the receive loop here, it will wait for one message, process it, send out another message, then wait for the other message, and then die. Because, well, again, as I've called it receive loop, because in the next round of programs, we'll actually turn it into a loop. Right now, we're not actually looping, but I wanted to keep the name consistent. So we have a Mike.url, and Mike.url is a little simpler because Mike similarly is going to start up a new process. It will say Mike has arrived and then enter into its receive loop function, which is not actually a loop yet. The newly spawned process will have its own PID, whatever that might be. We will then register that PID under the name Mike. So there'll be a registered name Mike. And again, so it will print out Mike has arrived, then it will go into this loop. It will wait for a message. Once it receives a message, it will send out another message to Joe. So Joe has to exist when we run this. We're going to start up Joe last for that reason. Joe sort of starts everything. He kicks everything off, and if he's running, if we tried to start up, well, the order matters. We'll see that. So this is Mike, and then there's also Robert. That's not Robert. There we go. I didn't say Earl. There we go. So Robert's very similar. The only difference, so Robert's going to receive a message, then send a message to Joe, and he'll also say Robert has arrived. If I look in this, you'll see here that ignore the ping pong things, but each of the three files we just looked at, the URL files, the .url files are the source files, and the .beam files are the compiled versions of those. I'm going to remove the compiled versions so you don't think that there's some trick up my sleeve that I've already set something up. We're going to compile these ourselves right now. So the way you start up the Erlang REPL, the read, evaluate, print loop, is simply typing ERL. So we'll do that now. So now we are in a shell. We are in a process, an Erlang process. It started up an Erlang system, a virtual machine, and it created one process just to handle our shell here. So we are, since we are in a Erlang process, we can, sorry, let's get that. We are in an Erlang process. We can find out our own PID, and the way we do that is by typing self. And now we have a self, and if we want to save that to a variable, we can save. We can make a variable, whatever it is. It just needs to start with a capital letter. So we're going to save that value in PID. If I say self again, I have not changed, so it's going to keep giving me the same value. Now, if I blow up intentionally here, if Erlang by default, if you run illegal code, it will blow up and it will kill your process. And other processes could potentially be responsible for noticing that and restarting you in a healthy way. But for the moment, I'm just going to kill myself by dividing by 0, which is illegal. So you see the exception, but it didn't spit us out of the REPL. What it did was it killed the process that we were in and started up a new process that we are now in. So if we look at self, we're no longer .83, we're now .88. So I'm going to store .88 here, and again, why did that not work? Oh, so this is another thing. This is actually different between Elixir and Erlang. In Elixir, the variable PID would have been rebound here, but in Erlang, there's no rebinding of variables. It is a truly, it's based on immutability. So once you bind a value to PID, you can't rebind a value to PID. There are ways in the shell to change that, but I'm just going to instead create a new variable called PID2. And I'll assign the new value of 91 to that. And you'll notice it killed the second process that we ran under 88 got killed as well because I tried to assign to a variable that had already been assigned to. So now hopefully if I say self, this one shouldn't blow up because it is remaining 91 at this point. So, okay, so let's send a message to ourselves at this point. So we can send a message to ourselves. We can type whatever we want. I'm going to say hello shell, but we could send any message. I forgot the period. Okay, so when you send a message, the return value is whatever this message was. This is different from the actual message being received and processed by the shell. The message is sitting in the shell's mailbox, but before I show that, let's send a second message. Hello, let's call it hello again shell, and I again forgot the period. So now at this point we should have two different messages in the mailbox. So let's look at that. There's a function there's an Erlang module which has a process info function. We can tell it we want to know about ourself, and we want to know the message queue length. And again, I need a period. You'll see that there's two messages in our own mailbox, and this should be the same as PID2 because we said PID2 is the PID for us. We can actually look at those messages like this. So you can see that the messages are sitting there in our mailbox, and one way we can get at them is by doing flush. If we do flush, it just flushes everything that's in the mailbox. So right now, if we go back to this, now the mailbox is empty because we flushed everything. Let's send a few more messages to ourselves. Let's call this hello number 3, and I need a period. Hello number 4, and hello number 5. And then we'll again look at our messages. Okay, so the messages are there. Now we're going to do a receive. We're going to create because we're in a process, we can have our process do a receive. And what we're going to do is we're going to get a message out of the mailbox. We pull one message out at a time, and then we're just going to return it. We're not going to do anything special with it. So we pulled the third message that we put in our mailbox. The first two we flushed. Then the third message we added, we just pulled it out. Now, I would think if I did receive again, I would get the fourth message out. For some reason, it doesn't seem to be working. And if anybody watching knows why, please let me know, and I'll post it in the room if I post this on YouTube. But I don't know why receive doesn't work again. So instead, I'm just going to show you that the messages are still sitting in the mailbox. There's something weird about I can't get at them again. So I'm just going to flush them here. Okay, now that we know how the REPL works, let's go back into the REPL and start up our Joe, Mike, and Robert files. So Earl. Okay, so first to compile a file, so remember we have joe.earl, and it's in this directory. So I'm going to say C for compile, Joe. You don't have to type the .earl part. So it seems to have compiled. Let's check that it actually compiled. M stands for module, so there is now a module named Joe, and there's some extra information. It shows you the exports call start and then module info, which was added automatically. Let's try calling module info. See what. So it added those to Joe, so we can say Joe module info, and you'll see that there's a 0 arity and a 1 arity function version. So the 0 arity gives you all the information. If you'd like to get a subset of the information, you can type in the atom associated with the key of what you're looking for. So in this case, for example, we could just look at the exports there. So when I said atom there, so if I put something inside of strings, that becomes a binary. A binary is just a list of numbers that gets interpreted as characters. If I don't put the string there, if I just say Joe, that is what's called an atom. And what an atom is that there can only be a single instance of an atom, and modules are all named after atoms. So Joe is an atom, Robert's an atom. Well, they're not yet because I haven't compiled it. If I actually say, tell me about the module Robert, it's not going to know anything about what I'm talking about. Because there is no Robert. Actually, did we just lose Joe, or is Joe still there? Joe, let's find out. So Joe's still there. Okay, so let's compile Robert and Mike. Mike and Robert. Okay, so now we've compiled the files, but we haven't actually used them. So the next step is to start them up. So right now there's no function. So there's no processes named Mike or Joe or Robert because we've loaded modules, which is code, but we've not actually executed it and started up a process. So if I say registered, it'll show me all the registered processes, and there's no process named Mike or Joe or Robert here. And we've asked our processes once they're spawned to be named with registered names, so they should show up here if they were running, and they're not showing up here. So let's start them and see if we can find them. So we say Mike start. So now we started Mike, and you'll see the string that we asked it to print when it started up is shown there. We can do the same with Robert. Now let's run this command again and see if they show up now. So Robert is indeed here. So Robert is now running and registered. And Mike is hiding here somewhere. There's Mike. There he is. So Mike and Robert are there, and Joe is not there because we haven't started Joe up yet. But let me also, at any time, you can also say processes. It'll give you a list of all the PIDs that are running. Not too useful in that format, but there are things you can do to get other information. You can also say I, and it will show you all of there's a lot of things running that we didn't start up actively, but they run automatically. Like there's logger, for example. So you can take advantage of the logger to log stuff. That's the kernel supervisor. We haven't talked about supervision trees yet, but we will in future episodes. And it will also show you the initial call that was run for each of these things. So the initial thing that this process 000 is a special process. The very first process that starts up is it calls a 2-arity start function. Init is a loop. It calls a loop, and it's a single one arity function, and the value it takes, the loop function is taking, is the state. And that's a very common pattern in Erlang and Elixir, where you start a process and you loop, and that process keeps looping, and each time through the loop, it's taking the final state of the loop and making that the initial state of the next loop. So it's a recursive data that gets saved every time the loop is called recursively. The state is persisted by passing it into the next invocation of the loop function. You'll also see that there's a supervisor here. There's various things going on. Let's see more. There's even more processes running. Anything interesting here? There's well, I'm not going to go through all of these right now, but you can get an idea. And there's Mike at the bottom there. Mike is there. And I have not yet seen Robert, but Robert should be, there's Robert at the very end. So Robert and Mike are both listed there, as are all the other processes that are currently running. So we can also say, where is Robert? Since Robert is running, there should be a PID associated with Robert, and we can say, where is Mike? Of course, if we say, where is Joe? We haven't started Joe yet. So if we say, where is Joe? We're not going to get, he's undefined. Another thing we can do is regs. I should have done this first, because you'll see that Mike is here, for example. Oop, there's Mike with 107. And let's confirm that that's what we found for Mike, 107. So you can look up all the processes using this regs, which presumably stands for registered processes. But let's do the thing. So we said earlier that Joe is the process that kicks off all the messages. So let's start Joe. We've compiled Joe, but we haven't started Joe. So let's start Joe and see what happens. Okay, so Joe announced that he had arrived, as did the other processes when they started. Then Robert received a message. Hello, Robert, from Joe, because Joe kicks things off. He sent the first message to Robert. Robert, upon receiving the message, sent a message back to Joe saying, hello, Joe, from Robert. At that point, Joe, once he receives that message, sends a message to Mike saying, hello, Mike, from Joe. And then Mike, receiving that message, responds to Joe. And because none of those functions that I called loop actually are loops, they were all completed at the point when they got to the end of their functions, and the function did not loop. So each of those processes did the things that they were supposed to do, and then when they got to the end, they then died. So if we now try to say, where is Mike? Mike is now undefined because Mike doesn't exist anymore. Similarly, Joe and Robert no longer exist because they have been turned off. So let's go on to a second version of this where, well, let me show you the second version first. So code, sorry, ls. So this is a new version, vi.joe.earl. So this is a different directory, but I've created the same modules again, and except they're a little different now. So instead of sending just a string, instead of sending just a string, I'm now sending what's called a tuple. So a tuple uses these braces, and you can put any elements you want inside. It's like a list, but the items don't have to be the same types of things. They can be anything. So in this case, the message is an altered version of the message we were sending before. We're just indicating that this is version 2.0 of our program. The difference here is that when Joe sends a message now, Joe is going to announce that it's coming from Joe. He's saying, this is from me. So he sends a message to Robert, but announces that it's coming from Joe. And when he receives a message, the message will have this, it will match a tuple, because we're now sending tuples from process to process. We can do whatever we want. Any Erlang data structures are valid, but we're choosing here to send two element tuples. The first element being the sender of the message, and the second element being the message itself. In this case, so now we're saying Joe 2.0 received a message from, and then we'll fill in the sender. So if it's coming from Robert or Mike, it will say Robert or Mike here. And then the second value we're filling in right here is the message itself. Again, Joe is going to expect a second message and record it, and then Joe will die. So, and I did similar changes in the others. I guess we can look at one more, vi mike.url. So Mike similarly is going to now be expecting to receive a 2-element tuple with the sender and the message. And when Mike sends a message, he will include himself as the sender, the first element of the tuple, alongside his message. So we can, let's see, we can load this up, and we'll compile Joe, compile Mike, and compile Robert, and then we will start them up. Start Mike. That did not work. What did I do wrong? Oh, it's Mike.start. Mike:*start. Right, of course. Robert. And again, I don't want to do, I want to save Joe till last because he kicks everything off. Joe. Start. And we see the expected messages, and we also see now that each recipient of a message is also, they're extracting out of the first element of the tuple is the sender of the message. And the sender is an atom. The message itself is a binary. So this is the atom that they're receiving, and this is the binary that they're receiving. And at this point, let's see if registered. They have all died. They're no longer. Where is Joe? Because we didn't ask them to stay along after they sent their messages and received them. We will in the next video. We'll go into the looping and how to keep a process alive. But I think we've covered enough for today, so I will stop here. I hope you've enjoyed this introduction to Erlang and the history of Erlang and the beginnings of Elixir. I hope you enjoyed the hands-on Erlang coding exercise. I'm looking forward to doing many more videos, hopefully much shorter than this one. There's a lot of ground to cover in this intro video, but I hope to put out a whole series of Erlang and later Elixir videos that sort of build progressively on top of what we've learned today. Now that I've introduced you to Robert and Mike and Joe, I think you can appreciate, I have a little small set of servers that I use for hacking around and playing with, and I think you will maybe now be able to appreciate my naming convention. I named my very first 3 machines Verding, Williams, and Armstrong in their honor. What they did is extremely compelling to me, and I just love Erlang and Elixir, and wanted to honor them. And it makes me happy just every time I think about the server names. I'm so appreciative of what they built and enabled for the ecosystem today. I want to share a few learning resources if you want to go deeper on Erlang. The first place you might want to look is on YouTube. Simon Thompson, who is a professor, I think he recently retired in England, taught a series of talks on Erlang, and he builds up progressively. They're excellent talks, completely free on YouTube. Also, once you finish those, you may want to consider, the University of Kent did a series. You can see 3 different playlists here. There's a Erlang Masterclass 1, 2, and 3. It's a whole series of videos, and that's Joe right there. I think Francesco Cesarini did some of these. They're excellent. Erlang has super documentation. It suggests here some books, many of which are free, some of which are paid. The documentation itself is excellent. They're basically online books explaining how Erlang works. I maintain a page on GitHub that I call My Tech Resources, and there's various pages, but I have one page, Elixir, which is full of Elixir and Erlang resources and there's a little smattering of stuff for other Beam languages. And finally, I would like to end this with some unsolicited advice. I'm hoping this will become a regular, hopefully much shorter series of presentations on Erlang and Elixir. This intro video obviously had to cover a lot of ground, so it's much longer than I intend for future videos. But at the end of each, I'd like to share some advice that I've picked up over the years in this industry that isn't necessarily related to Elixir or Erlang. And since this video is so long, I'm going to keep this really short today. My advice is to not drink soda or tonic or pop or whatever you want to call it, depending on where you grew up. I drank way too much soda for the first 25 years of my life, and my teeth suffered for it, as did my stomach. And in the middle of a run one day, I couldn't run any further. I literally could not move another step. And went to see the doctor. He told me to stop drinking soda. I did. The next 25 plus years have been way better. My teeth are happier. My body's been happier. It's unbelievable how much soda. Forget the carbonation. The acid is horrible for your teeth, but the sugar alone is horrible for your body. And apparently there's like 29 different sodas at least that this article points out. Each of them, a can of it has more sugar in it than 4 donuts. So I urge you to try to reduce the amount of soda that you're drinking, and ideally stop drinking soda. I like to keep a bottle of water with me at all times. And if you have whatever you keep within arm's length of you, whether it's like M&Ms or healthy stuff, that's what you're most likely to eat. The harder it is to get to it, the less likely, the less you see something. Things that are bad for you, you want to keep out of sight and out of reach. Things that are good for you, you want to keep within sight and within reach. So by keeping water, or I drink coffee and tea, those are great. I was drinking soda for decades for the caffeine primarily. I get all my caffeine now through coffee and sugar and tea, and I drink lots and lots of water, and I'm happy I haven't had soda in decades, and I urge you to do the same. It's a great way to be healthy. So thank you for coming. I look forward to doing more of these Erlang and Elixir videos, and hope you'll come back for more. Cheers.